The Science of Airplane Flight. Fasten your seatbelts. You're about to take to the skies. Flight 001, you're clear for takeoff. Roger that. Airplane flight is more popular than ever. Billions of passengers fly each year. Pilots make flying look easy, but it's not. There are many invisible forces of physics at play during each flight. How does it all work? To find out, let's talk to some scientists at NASA, or the National Aeronautics and Space Administration.
Hi, my name is Joe Chambers. I'm a retired aeronautical engineer, retired from the NASA Langley Research Center after a 36-year career in aeronautics.
Aeronautics is the science of airplane flight.
I find that children your age ask questions that in many cases are more difficult to answer than adults.
So let's start with the basics. How does physics play into airplane flight?
The four forces acting on an airplane in flight include its weight, which acts downward to pull it back down to the earth. That force has to be overcome by aerodynamic lift, which lifts the aircraft and enables it to go to altitude. Lift is the vertical force produced by an aircraft, primarily the wing, and it's influenced by the shape of the wing. Another important force acting on the airplane is what we call aerodynamic drag. That's caused by the resistance of the air as the aircraft flies through the air. It doesn't pull, it just resists the forward motion of the airplane. And that force, of course, has to be balanced by thrust, which is produced by the engines.
Thrust makes the engines of a plane go fast. Commercial jets can fly at over 600 miles an hour. They fly at pretty high altitudes too, at over 30,000 feet above the ground. Some planes go even faster. They're called supersonic planes because they fly faster than the speed of sound, which is about 760 miles per hour at sea level.
We call the fastest planes supersonic airplanes because they travel faster than the speed of sound, and they get people to their destination a lot faster. My name is Christine Darden, and I worked at NASA Langley Research Center for nearly 40 years. The problem that I have worked on in my career is that airplanes that travel faster than the speed of sound create a sonic boom that people on the ground can hear. Sonic booms are really loud. It sounds like a boom or a loud crack. And my work was to try to see if we could reduce that sonic boom so they would not be this disturbing byproduct of supersonic flight.
We usually don't see supersonic planes in the air today because of the sonic boom noise. A sonic boom is a shock wave that works like this.
As you blow up a balloon, you're blowing into it, the pressure is getting higher and higher into the balloon. And that's, of course, why it gets bigger, because you're getting more molecules inside the balloon. If I took a needle or pen and popped that balloon, there is an immediate shock wave set up in all directions. It's like a sphere going out from that balloon in all directions with this high pressure air. And so it is going toward you. As this boundary of this sphere goes across your ear, you're getting an instantaneous change in pressure from the normal pressure to the high pressure that was in the balloon. But that change in pressure instantaneously is what you hear. And that's the same thing that happens with an airplane when it is going faster than the speed of sound. It's almost like an ice cream cone on the nose of the airplane, and all of the molecules that have been disturbed by that airplane and pushed out of the way and the higher pressure air are within that cone. And this cone goes all the way to the ground. So you hear the instantaneous change between the normal air and the air that has been inside that cone. And that's what you hear when you hear a sonic boom. One of the approaches we took to trying to change the sonic boom was to see if shaping the airplane differently would impact the sonic boom. And so sometimes you find the airplane might be longer. One of the ways that we test out our ideas about how to reduce the sonic boom is to build models of the designs that we think might work, and we would put that model in a wind tunnel and measure the pressures coming off that model. In the wind tunnel, the air is actually blown past the model itself, which gives pretty much the same effects. And we measure data points that we want inside the wind tunnel. That's a lot cheaper than building a big airplane, flying it through the air, which is prohibitively expensive.
Wind tunnels have been popular ways to test airplanes since the 1930s. Many tests are done at NASA's Langley Research Center in Hampton, Virginia.
One of the most famous wind tunnels was the Langley full-scale wind tunnel, which was enclosed in a building as long as a football field, and it had a test section where full-scale aircraft were tested. The test section measured 60 feet across and 30 feet high, which is immense. Ran at an airspeed of 100 miles an hour and operated for over 80 years.
Other wind tunnels are smaller, and the air travels faster. Scientists use the smaller wind tunnels to test new supersonic plane designs. They haven't solved the sonic boom problem yet, but they're getting close.
We're hoping for a lower rumble, maybe, that would not upset people. That's ultimately the goal, that you want to benefit society with the scientific principles and advances. You want to show how that benefits how we live.
So kick back, relax, and enjoy the ride.